Tonight's journey drifts into the heart of Scorpius, where Antares glows as a vast red supergiant quietly expanding and shedding its outer layers into the dark. In this calm, slow documentary, the surface stays gentle, while the deep interior keeps time in shorter and shorter steps, shaping shells of dust and faint arcs across a whole light year of space. If this kind of science sleep voyage is your refuge tap, like to support the channel and subscribe for more long-form cosmic stories designed to carry the mind into rest. Now, let the red lights soften, let the distances widen. Antares hangs in Scorpius as a deep red presence that looks calm while its outer layers drift outward. The expansion is real, yet it comes from an interior that grows denser and more tightly bound. In that region, the star's visible edge looks like a soft rim that fades rather than a hard line. The first unlock is simple. A supergiant can grow larger because its core contracts and heats, while its surface loosens and swells. The scene begins with a red disk against blackness. The centre glows warmer and steadier. The limb dims into a thin reddish haze. A faint veil surrounds it as if light passes through tinted steam. Antares belongs to the class called red supergiants. A red supergiant is a massive star with a vast cool outer envelope. Cool in this context means red light dominates the glow. Like iron left to cool from white to cherry red, the colour shifts while heat still remains. Like a banked coal that looks quiet, energy keeps flowing upward from deeper layers. The reason it matters is scale. A swelling envelope changes how the star sheds mass and how it approaches its final stages. A single number anchors the size without forcing precision. Antares reaches about 700 times the Sun's radius. That span is like enlarging a small marble into a sphere wider than the inner region where rocky planets typically circle. The second unlock follows at once. Such size is not a rigid body. It is a layered atmosphere held by a balance that is always adjusting. The physical detail is written into the glow. The brightness drops toward the edge because light escapes from higher and cooler layers there. The rim looks dimmer because the path through thin gas is longer and more transparent. The star therefore shows a gradient, not a painted circle. Another visual anchor settles in slowly. A red horizon curves away with wisps that drift outward and then dissolve. The wisps are not smoke. They are tenuous gas where atoms and dust scatter the light. Expansion in a supergiant is not a steady inhale. It is a slow reorganization of pressure and gravity. Gravity pulls inward everywhere. Pressure pushes outward where heat and motion carry energy. When the core runs low on the easiest fuel, it contracts. Contraction raises the core temperature. That added heat powers fusion in shells around the core. The envelope receives energy in a different way than before. It puffs outward as the layers adjust to the new pattern of heating. The payoff is a quiet one. Expansion does not mean the star becomes less active inside. It often means the interior becomes more extreme while the surface becomes more diffuse. A new scene opens inside the red haze without becoming technical. Layers appear like faint bands that blend into one another. The deeper bands look brighter. The outer bands look darker and thinner. The boundary between them is not sharp. It behaves like a coastline of light that shifts with each slow pulse of heat. Convection shapes the outer envelope. Convection is heat moved by rising and sinking gas. The definition is brief, yet it changes the picture. Rising regions carry warmth upward. Sinking regions return cooler material downward. Like warm air lifting from sunlit ground and cooler air sliding in to replace it, circulation forms broad patterns. Like boiling water where large eddies roll under the surface motion, keeps the outer layers mixed. The reason it matters is the face of the star. Convection creates patches of slightly different temperature. Those patches alter the brightness in slow, irregular ways. The visual anchor becomes more specific. Darker red-brown regions drift across the disk. Brighter regions bloom and fade without any strict rhythm. The movement is slow on a human clock, yet it is fast on a stellar clock. The scale shift arrives softly. A single rising cell can span a large fraction of the visible surface, while the gas inside it changes in hours to days. The star looks like one object, yet it behaves like an atmosphere stretched to enormous size. Another payoff lands without emphasis. A swollen envelope is easier to disturb. When the surface gravity weakens across a huge radius, gas can escape more readily. That leads to a wind that carries material away. The wind is not a jet. It is a broad outflow that thickens the space nearby with atoms, molecules, and dust grains. The physical detail shows itself as a faint halo. The halo is brighter at some angles because dust scatters red light more efficiently along longer paths. A new image settles in. Thin filaments drift outward like strands of seafoam pulled by a gentle current. The strands break apart. They become a smoother veil farther out. The story remains calm, yet it reaches a limit of intuition. In ordinary life, surfaces are boundaries that can be touched. In a red supergiant, the surface is a zone where light finally escapes. At this distance, a measurement would depend on which kind of light defines the edge. In some wavelengths, the star looks smaller and sharper. In others, the atmosphere looks larger and more diffuse. A signal would blur the boundary because the gas is semi-transparent and constantly moving. The limit is observational and conceptual at once. Radius is not a single fixed skin here. It is a choice of threshold in a fading glow. Another payoff follows from that limit. The expansion can be described without needing a perfectly defined edge. The key is the trend. The envelope becomes more extended over time. The density in the outer layers decreases. The star's light filters through more material before it leaves. The red colour deepens because the outer layers are cooler than the interior. The final visual anchor for this section arrives as a slow close. The red disk softens. The limb dims into a thin, floating gradient. The surrounding haze thickens and thins in uneven arcs. Nothing snaps or flares. Everything drifts. The transition stays gentle. The next step is distance and light travel, since the view of Antares is always delayed. In that region, light behaves as a quiet messenger that carries the history of the swelling layers outward into dark space. Antares appears steady because light arrives as a calm stream, not as a sudden report. The view is always delayed, so the red glow describes an earlier Antares rather than the exact present. At this distance, a faint pulse of brightness would be a message that has already travelled for a very long time. The first unlock is time hidden inside distance. The star can swell and shed gas today, yet the light now reaching space nearby began its journey long ago. Antares lies about 500 light-years away, like a signal taking about 5 centuries to arrive. A light-year is the distance light travels in 1 year. Like a slow tide that keeps advancing even after the wind stops, light continues once it is released. Like ripples of brightness spreading through darkness without slowing, the travel is constant and patient. The reason it matters is interpretation. A change seen now belongs to an earlier chapter of the star's evolution. A visual anchor settles in. A thin shell of red light expands outward from Antares in silence. It moves through empty blackness. It crosses faint dust lanes that look like soft smoke yet remain cold and still. The shell does not thicken as it travels. It simply spreads wider, so the same light must cover more space. The second unlock follows from that spreading. Brightness fades with distance because energy is shared across a larger sphere. The fading is not a failure of the star. It is geometry. A small lamp seems weaker when it is far away. Antares is no lamp, yet the rule still holds. The red point therefore carries 2 stories at once. One story is the star's power. The other story is the long stretch of space in between. A new visual anchor arrives gently. A corridor of dark dust divides the star field into bands. The red point sits behind it. The dust does not form a wall. It forms a thin mist of grains and molecules. Those grains scatter shorter wavelengths more strongly than longer ones. The physical detail appears as a colour tilt. The light that survives the journey looks redder. The light that is lost is the bluer part that scatters away. A small payoff comes without any label. Redness can rise from the star's cool surface and also from the path it takes. The same hue can therefore mix source and journey. A third concept enters with care as a tool of thought rather than a tool of metal. Parallax is an apparent shift caused by a changed viewpoint. Like a near cloud sliding against a far mountain ridge, a closer object seems to move more. Like a drifting dust knot crossing a distant nebula, the near feature shifts faster against the background. The reason it matters is distance. If the shift can be measured, distance can be inferred without guessing the star's true size. A quiet limit appears here stated softly and clearly. For distant stars, the parallax shift becomes extremely small. A measurement would struggle because the background itself is not perfectly fixed. The star field has its own slow motions. The result depends on long baselines and careful models. Uncertainty therefore grows as distance grows. Another payoff follows from that limit. Distance estimates are often a blend of methods. Parallax helps when it is large enough. Other methods rely on brightness, color, and motion patterns. Each method carries its own assumptions. The assumptions can drift when dust thickens, or when a star varies. The view of Antares therefore includes a margin of softness like a horizon, seen through heat haze. A main analogy holds the section together. Light behaves like an echo that arrives long after the first event. The echo keeps the shape of the original sound, yet it also carries the imprint of the canyon. In space, the canyon is the interstellar medium. It is thin, yet it leaves fingerprints through scattering and absorption. The echo image keeps the tone calm. It also keeps the logic clear. A signal would never be purely about the source, it would also be about the path. A new visual anchor returns to the star itself. The red point sits within the pattern of Scorpius. Nearby stars appear sharper and whiter. Farther ones look dimmer and more crowded. The field seems flat, yet depth is hidden inside it. That hidden depth is a scale shift that unfolds in stages. A short movement along a planetary orbit changes viewpoint by a modest amount. That modest change can reveal distance across hundreds of light years. Another payoff lands quietly. Small motions can unlock vast scales when geometry is patient enough. The rhythm remains slow, the star's light drifts onward. Dust grains turn some of it aside. Some light is absorbed and re-radiated at longer wavelengths. The journey becomes a gentle filter. The filter does not choose, it only follows physics. A limit of observation returns in a different form. Even if distance were known perfectly, the star's edge would remain hard to define. In some wavelengths, the atmosphere looks extended. In others, it looks tighter. A measurement would therefore change with the kind of light considered. The boundary is partly real and partly a choice of threshold. Another payoff follows from that boundary problem. The idea of size must be treated as a zone rather than a line. The star becomes a set of layers where light escapes at different depths. The eye of the mind moves from travel to structure. A final visual anchor closes the section. The red point brightens slightly as dust thins along one line of sight. The rim of the star is not seen directly, yet the notion of a fading edge becomes present anyway. The transition stays gentle. The next step turns from the long road of light to the star's own outer layers. In that region, the edge of Antares behaves as a gradient where glow dissolves into space. Antares does not end at a crisp border, because its outer layers thin into a fading glow. The star's surface is a zone where light finally slips free through gas of changing density. In that region, brightness falls toward the edge in a smooth gradient. The first unlock is that size becomes a soft threshold, not a solid wall. A red supergiant carries an atmosphere so extended that the visible rim is a dim veil. The visual anchor forms as a slow close view. A broad red disk hangs in darkness. The center looks fuller and steadier. The limb looks like a faint ring of embers seen through gauze. The ring is not a separate structure. It is the same light seen through a longer path of cooler gas. Limb darkening explains this fading edge. Limb darkening is dimming toward the edge of a star's disk. The definition is short, yet it changes the picture at once. Like looking through deeper water near a pool's far side, the view passes through more material. Like a candle flame that looks thinner at the sides, the brightness drops where the line of sight skims the cooler layers. The reason it matters is measurement. The apparent radius depends on how the edge is defined in a gradient. The physical detail stays concrete. The glow transitions from warm red to darker red. It then dissolves into near black. No sharp boundary appears. The star's atmosphere is stratified. That means properties change with height. Temperature falls outward, density falls outward. Opacity also changes because atoms and molecules absorb light differently in different bands. The second unlock arrives gently. Different kinds of light leave from different depths. In one wavelength, the star looks slightly smaller. In another, it looks slightly larger. A single number anchors scale without forcing precision. The surface region spans tens of millions of kilometers in thickness. That span is like widening a city street until it becomes a whole province of haze. The scale shift remains calm. A feature that seems like a thin rim from far away becomes a vast vertical distance in the atmosphere itself. A new visual anchor scene appears without repeating the earlier ones. The disk is seen as a stack of translucent sheets. Each sheet glows faintly. The outermost sheets are almost invisible. Light leaks through them in slow layered fashion. The analogy holds the section together. The boundary behaves like the edge of fog around a lamp. The lamp seems to end where the fog thins enough. Yet the glow continues outward in a diminishing halo. The halo does not have a single ending point. It depends on sensitivity and contrast. The payoff arrives quietly. This is why expanding can be described without needing a single sharp radius. If the atmosphere becomes more extended, the zone of escape moves outward. The star looks larger in the same way a fog halo looks larger when mist thickens. A limit of observation appears and is named clearly. At this distance, resolving the rim directly is difficult because the disk is tiny in angular size. A measurement would be limited by resolution and by the atmosphere's own motion. The rim also changes with wavelength because opacity changes. The result is that a single reported radius hides choices and uncertainties. Another payoff follows at once. The safest description focuses on orders of magnitude and trends. The outer layers are diffuse. The edge is a gradient. The size is real, yet it is defined by where light escapes in a fading atmosphere. The story moves inward without becoming dense. Photons begin deeper and scatter outward. Scattering is light redirected by particles. The definition stays brief. Like sunlight diffusing in milk, the path becomes a soft blur rather than a straight beam. Like headlights in mist, glow spreads beyond the sharp source. The reason it matters is the rim. Scattering and absorption shape how quickly the brightness drops with the angle. The physical detail returns as texture. The limb is not only dimmer, it is also smoother because many paths mix together. A subtle transition of colour and brightness is therefore expected. The star's expansion changes this balance. As the atmosphere puffs outward, density in the outer layers drops. Opacity can drop in some bands and rise in others. Dust can form in cooler regions farther out. Dust adds a faint halo by scattering and re-emitting light at longer wavelengths. The visual anchor deepens. The ember's ring becomes a wider, softer aureole. It looks like a thin blush around the disk that fades gradually into black. Another payoff lands softly. A swelling envelope can increase the apparent size even when the core tightens. The appearance depends on where the light last interacts strongly with matter. The scale shift widens once more. A change in density over a small fraction of the star's radius can shift the visible edge by an enormous distance. That change can happen over years to days while the deeper evolution unfolds over far longer times. The last scene settles into calm closure. The red disk remains. The rim remains a fading gradient, not a line. The halo remains a delicate haze. The transition stays gentle. The next step turns from defining the edge to explaining what stirs the outer layers. Convection and slow surface patterns become the next checkpoint. Antares shows a face that seems to drift because the outer gas is always in motion. The mottled patterns come from convection that moves heat upward in giant cells. In that region, the surface is not a calm skin, it is a slow field of rising warmth and sinking coolness. The first unlock is that brightness variations can be atmospheric weather on an enormous scale. The visual anchor settles as a close view of the red disk. Dark patches lie like broad stains. Brighter patches glow like shallow pools of light. The edge remains softly dim. The centre remains fuller and steadier. The patches shift without any strict rhythm. Convection remains the main engine of this shifting. Convection is heat moved by rising and sinking gas. Like a pot of thick soup that rolls in wide swells, the surface rearranges as warmer material rises. Like warm air lifting from a sunlit road, columns ascend and spread. The reason it matters is transport. In a supergiant, radiation alone cannot carry energy through the outer layers fast enough. Motion must help. The physical detail becomes specific. The rising regions expand as they climb. Expansion cools them. Cooling changes what kinds of atoms and molecules absorb light. The result is contrast. Some areas look slightly darker because they absorb more at the wavelengths that escape. Some areas look brighter because the gas is a little warmer and more transparent. A small payoff arrives quietly. The face is not painted by spots that stay fixed. It is painted by moving layers that change as they rise and fall. A single number anchors scale with safety. One convection cell can span about a third of the star's diameter. That span is like covering a whole continent with one slow weather system. The scale shift follows at once. What looks like a patch on the disk is larger than many planetary orbits would be. Yet the gas inside that patch still behaves like gas. It expands. No. As it cools, it mixes. It drifts. Another visual anchor arrives in a different register. A dark lane stretches across the disk. It curls at the end. It breaks into two softer shadows. The shadows thin out as they move toward the rim. The motion is not fast. It is steady on the scale of days and weeks. The payoff is direct. The star can change its appearance without changing its identity. The overall luminosity can remain similar, while the surface texture evolves. This leads to gentle variability. Variability is change in brightness over time. Like a lantern seen through thin moving mist, the light seems to pulse even when the flame is steady. Like sunlight through slow clouds, brightness shifts without any sharp beats. The reason it matters is inference. Variability offers clues about the size and structure of the envelope. The limit of observation arrives softly and clearly. At this distance, surface detail is hard to resolve because the disk is tiny in angle. A measurement would often rely on indirect signals. The signal mixes true surface changes with the effects of dust and wavelength choice. Models must guess the three-dimensional pattern from a two-dimensional glow. The limit is therefore resolution and interpretation. It is hard to say which patch is a single cell and which patch is many cells blending. Another payoff follows from that limit. Even uncertain patterns can confirm a key truth. The outer layers are turbulent and structured. They are not smooth. The atmosphere behaves like a thick ocean of gas with slow, giant swells. A new physical detail joins the scene. Near the limb, the contrast softens because light comes from higher and cooler layers there. The same patch looks different at different viewing angles. The rim darkening blends features into a smoother edge. This makes the star seem calmer at the boundary. The centre remains the best window into deeper layers. The narrative shifts in scale again. A bubble of rising gas may travel a vast distance in the envelope. At the same time, the star as a whole evolves over much longer times. The surface patterns are quick brushstrokes compared with the slow story of burning and mass loss. The main analogy holds steady through the end. The surface behaves like slow waves on a Red Sea. The waves do not crash. They lift and settle. They carry heat and return it downward. The sea has no shore. It fades into a mist at the edge. The final visual anchor becomes quiet closure. The red disk turns slightly mottled. A bright region drifts and dims. A dark region thins into the background. The overall glow remains. The transition stays gentle. The next step turns outward from patterns on the face to the steady leak of material. A wind and a surrounding envelope become the next checkpoint, Antares releases material so gently that the loss can feel like a slow fading rather than an event. The star sheds mass because its outer layers are loosely held and easily pushed outward by light and motion. In that region, the boundary is not only a gradient of brightness, it is also a place where gas begins to drift away for good. The first unlock is that an expanding envelope makes escape easier. Surface gravity weakens across a huge radius. Pulsations and convection add small lifts. Dust can form in cooler pockets and catch starlight. Those effects together can tip gas outward into a wind. The visual anchor begins as a red glow surrounded by a faint uneven halo. The halo looks thicker on one side and thinner on another. Filaments curve outward like soft ribbons. The ribbons fray as they go. The fraying is physical. Density drops with distance. So, light that passes through becomes more diffuse and red. Mass loss is the key concept, and it stays simple. Mass loss is the star losing gas into space, like a dandelion releasing seeds in calm air. The star does not throw material in one burst, it lets it drift. Like flour dust rising when a bag is opened, particles lift and spread into a widening cloud. The reason it matters is destiny. Losing mass changes what remains for the core to support. It also shapes the space around the star long before any final collapse. A single number anchors the outflow without chasing precision. Antares can lose around 1/1,000,000th of a solar mass each year. That is like spilling a large lake into open ground one drop at a time. The payoff arrives quietly. Even a slow leak becomes substantial over thousands of years. A wind that seems delicate can build a large envelope. The scene moves closer. The outer atmosphere looks layered. Some layers are smoother. Some layers show arcs where ejections were stronger. The arcs are not rings of solid matter. They are shells of slightly higher density. They form when the wind is not perfectly steady. A gentle scale shift appears. A small change in pressure deep in the envelope can alter a region larger than many planetary systems. Yet the change begins as a subtle imbalance in gas and radiation. Radiation pressure is the push from light on matter. Like sunlight pushing a thin sail, photons carry momentum that can nudge particles outward. Like wind tugging at a hanging curtain, a steady stream can shift a loose layer over time. The reason it matters is dust. Dust grains feel the push more strongly than single atoms. If dust forms, it can drag surrounding gas outward by collisions and coupling. The physical detail becomes vivid. Tiny grains appear in cooler zones. They tint the light. They scatter and absorb. They turn a clean gradient into a broader halo. A new visual anchor arrives distinct from earlier scenes. A faint spiral-like eddy is traced in the surrounding haze. The spiral is not a rigid coil. It is a pattern of density shaped by flow and local instabilities. The analogy for this section stays unique. The outflow behaves like breath on cold glass. At first it is a small fog. Then it spreads and thins. The edge is never sharp, it fades. The payoff lands with that image. The wind is not a river with banks. It is a fog of gas and dust that thickens near the star and fades outward. A limit of observation is stated softly and clearly. At this distance, the surrounding envelope is faint. A measurement would depend on sensitivity and wavelength. Some material is cold and mostly visible at longer wavelengths. Some material is warm and glows in different bands. Models must infer density from brightness, yet dust properties can vary. The limit is therefore indirect inference and uncertain grain composition. Another payoff follows at once. Even with uncertainty, the presence of an extended halo confirms ongoing loss. The uneven arcs suggest variability in the wind. The layered look suggests that the outflow carries memory of past conditions. The narrative moves through a checkpoint toward consequences. Material leaving Antares does not vanish. It enters the interstellar medium and mixes slowly. Mixing is not fast. It is a long drift through sparse space. The scale shift widens again. A grain that forms in a cool pocket near the star can travel for centuries while the star continues evolving for far longer. The grain may later join a distant cloud. That cloud may later collapse into new stars and planets. The connection remains calm and non-dramatic. Another visual anchor settles near the end. The red star sits inside a faint cocoon. The cocoon has a brighter inner rim and a smoother outer fade. The inner rim looks like a soft boundary where the wind is denser. The outer fade looks like breath thinning into air. The transition stays gentle. The next step turns inward again. If the outer layers are escaping, the interior must keep balancing gravity and pressure in a changing way. The following checkpoint moves toward the star's inner stability and the quiet tension in its core. Antares keeps a quiet stability because gravity and pressure match each other moment by moment. The balance is temporary, yet it lasts because the core tightens as the envelope loosens. In that region, the star behaves like a layered structure held by two opposing trends. The first unlock is that expansion outside can coexist with contraction inside. Hydrostatic equilibrium is the main frame. Hydrostatic equilibrium is balance between inward gravity and outward pressure. Like a tall stack of cushions that holds shape when the load matches the spring, the star stays intact while forces match. Like a deep pile of snow that compacts below while the surface stays fluffy. The interior tightens even as the outer layers remain diffuse. The reason it matters is control. When the balance shifts, structure changes quickly compared with earlier stages. The visual anchor begins as a slow descent through the star's layers. The outer haze is dim and thin. Beneath it, the glow becomes steadier and warmer. A boundary appears as a gentle change in texture rather than a line. Convection fades and a smoother zone takes over. The physical detail is a gradient of brightness and density. Each step inward feels like moving into thicker air. The second concept enters as the driver of change. The core contracts when fuel conditions change, and pressure support must adjust. Contraction is not a collapse into darkness. It is a tightening that raises temperature and pressure. The payoff is simple and immediate. A contracting core can supply energy that helps the envelope swell, even while the core itself shrinks. A single number anchors the scale of the hidden center. The core spans roughly the size of Earth's orbit. That size is like placing a whole inner planetary region inside a zone that remains unseen from outside. The scale shift lands gently. The visible disk is vast, yet the decisive physics happens in a much smaller interior volume. A new visual anchor takes shape. Inside the red body, a bright inner region sits like a glowing kernel. Around it, a softer shell glimmers, then fades into the cooler outer envelope. The shells do not look like walls, they look like nested gradients. Each gradient marks a change in temperature and density. The analogy for this section stays unique. The star behaves like a slow fountain under a heavy lid. The fountain's push is pressure from heat. The lid's weight is gravity. When the push rises or the weight shifts, the shape of the fountain changes. The payoff follows from that image. The envelope can lift outward. When pressure support is redistributed, even if the deepest parts become more compact, a limit of intuition arrives and is named clearly. In everyday objects, a shrinking center usually pulls the outer parts inward. In a star, energy transport changes the outcome. A simple mental picture fails because pressure depends on temperature and composition. The limit is therefore model intuition. The true behavior must be inferred from structure equations and indirect signals. A second limit of observation joins it softly. The core cannot be seen directly. A measurement would rely on surface brightness pulsations and spectra. Those are indirect. They can be influenced by dust and by the extended atmosphere. The result is that interior conditions are reconstructed, not observed. Another payoff lands gently. Even with indirect data, the need for a contracting core is robust. The star must keep producing enough pressure to oppose gravity. When fuel becomes harder to burn, contraction supplies the extra heating. The narrative moves through a checkpoint from balance to tension. The outer envelope remains loosely bound. It continues to lose into mass. That loss reduces the weight pressing on deeper layers. Yet the core grows denser as it contracts. The star therefore drifts toward a state with stronger contrast between inside and outside. The physical detail returns as layering. The density changes sharply with depth, the pressure rises inward, the temperature rises inward. The outer layers remain cool enough to glow red. The inner layers remain far hotter yet hidden. The scale shift widens again. Changes in the core can occur over years to centuries in late stages. Meanwhile, the overall appearance can drift more slowly through the long travel of light. A quiet transition of rhythm appears. What seems steady from afar is a superposition of slow swelling outside and tightening inside. A final visual anchor closes the section. The red disk remains calm. Beneath it, imagined layers compress into a smaller, brighter kernel. Around that kernel, shells of energy flow outward through a vast envelope. The scene does not sharpen into drama. It remains a steady structure under steady laws. The transition stays soft. The next step moves closer to the deep interior processes that reconfigure the star. Shell burning becomes the next checkpoint where different layers ignite in sequence. Deep inside Antares, heat does not come from one place because fusion shifts into layered zones. The star burns in shells, so different depths act like different furnaces working at once. In that region, structure becomes nested, and the envelope responds to what happens below. The first unlock is that late-stage burning rearranges the interior without needing a single central flame. Shell burning is the key idea. Shell burning is fusion occurring in a layer around the core. Like a set of stovetop burners turned on beneath stacked pots, energy appears at several depths. Like rings of warm water in a layered spring, heat rises from multiple bands. The reason it matters is stability. Each active shell changes pressure and temperature profiles above it. That change can puff the envelope outward and also drive stronger variability and mass loss. The visual anchor begins as a slow cutaway view. A bright inner kernel sits at the center. Around it, thin glowing bands form concentric layers. Between bands, darker gaps appear where fusion is weaker. The bands are not rigid hoops. They are zones where conditions favor certain reactions. The physical detail stays clear. Density rises sharply toward the center. Temperature rises even more steeply. A boundary appears where one shell ends and another begins. The boundary is a gradient rather than a wall. The second concept enters with care. Degeneracy pressure becomes important in very dense cores. Degeneracy pressure is resistance from crowded particles. Like a packed theatre where no more seats exist, matter resists being squeezed further. Like a jar filled with dry rice grains can shift only so much before the whole pack stiffens. The reason it matters is pacing. When normal thermal pressure is not the only support, contraction and heating can behave in unfamiliar ways. A small payoff arrives quietly. The core can become denser without immediately expanding again because compression energy is stored in different forms of pressure. A single number anchors the layering without crowding detail. The active fusion shells occupy a region roughly the size of Earth's orbit. That is like fitting multiple glowing layers inside the space where rocky planets would typically circle a smaller star. The scale shift follows smoothly. The visible red disk spans a far larger volume, yet the decisive layering sits in an inner zone. That inner zone influences everything above it through pressure waves and energy flow. The story moves through a checkpoint from core to envelope. Energy from a shell travels outward. Some energy moves as radiation. Some energy triggers convection in the overlying layers. Each shell therefore acts like a change in the thermostat for the envelope. The physical detail returns as motion. A pressure disturbance begins deep inside, it spreads outward, it weakens as it climbs. It reaches the lower envelope and alters how gas rises and falls. The surface may then brighten slightly or dim slightly as conditions shift. Another visual anchor appears. The concentric layers look like faintly glowing onion skins. The outer skins are thicker and cooler. The inner skins are thinner and more intense. The glow is not uniform. It flickers subtly along each band because conditions are never perfectly even. The main analogy stays unique and quiet. The interior resembles a stack of slow-turning gears made of heat. The gears do not spin fast. They transmit influence from one layer to the next. The payoff lands from that image. Changes do not need to race to matter. They only need to persist long enough for the envelope to adjust. A limit of observation arrives softly and precisely. The layered burning cannot be seen directly because the envelope is opaque. A measurement would rely on surface variability spectra and models of internal transport. Those signals can be ambiguous. Different interior structures can produce similar surface patterns. The limit is therefore indirect inference and model degeneracy. Another payoff follows at once. Even without direct access, the shell picture explains multiple clues at once. It explains why the envelope can swell while the core tightens. It explains why mass loss can strengthen as the star evolves. It explains why variability can become complex rather than periodic. The narrative widens in time without raising intensity. Shell burning stages are shorter than the long early life of the star. The scale shift is gentle but clear. A phase that lasts hundreds of thousands of years can still be brief compared with millions of years before it. Yet on a daily scale, the star still looks steady. Light arriving from far away smooths out rapid internal changes. Another visual anchor steadies the pace. The cutaway layers remain nested. The brightest inner band slowly shrinks in relative size as the core contracts. The next band brightens slightly as it takes over more of the energy output. The outer layers respond by expanding and cooling. The surface redness deepens. The rim stays softly darkened. The section closes with a calm transition. Shell burning sets the stage for a new kind of timekeeping inside Antares. The next checkpoint turns to pacing and uneven clocks where late stages speed up and intuition about stellar time begins to fail. A red supergiant keeps time in uneven pulses, where long calm phases end in shorter, faster chapters. The late stages speed up because each new fuel yields less energy and demands higher temperatures. In that region, the same star can feel steady on the surface while its interior clock accelerates. The first unlock is that stellar time is not a smooth flow. It is a staircase of stages with steps that shorten near the end. The visual anchor begins with a slow view of the layered interior. The outer envelope glows red and quiet. Beneath it, shell zones shimmer more intensely. The deepest core looks like a small bright knot behind a veil. The physical detail is layered thickness. Outer layers are broad and diffuse. Inner layers are thinner and sharper in gradient. Nuclear timescale is the first concept, and it stays plain. Nuclear timescale is how long fusion can power a stage. Like burning a thick log versus burning paper, the rate changes with what is being consumed. Like a pantry that shifts from sacks of grain to handfuls of spice, the remaining fuel becomes harder to use. The reason it matters is pacing. Hydrogen burning can last for millions of years. Later burning stages can be far shorter. A single number anchors this contrast safely. Hydrogen burning lasts about 10 million years in a massive star. That span is like a coastline eroding grain by grain across an age of quiet waves. The scale shift lands gently. 10 million years is long enough for continents to drift. Yet it can be only the opening portion of a massive star's life. The story then narrows inward. When the core moves beyond its longest fuel, the next fuels require higher temperatures. Higher temperatures raise reaction rates. Higher rates consume fuel faster. The star therefore changes its interior conditions more quickly. The payoff arrives quietly. Speeding up is not a choice. It is the consequence of needing hotter conditions for later reactions. Another visual anchor takes over. The interior layers look like a stack of dim lamps, each one turning on for a time and then fading. The outermost lamp stays on the longest. The inner lamps glow more fiercely, but for less time. The analogy for the section stays unique. The star resembles a long night where candles are replaced by smaller, brighter flames. Each replacement gives strong light but burns down sooner. The payoff follows from the image. Brighter internal power does not guarantee longer stability. It can mean the available fuel reservoir is smaller or harder to sustain. The second concept enters with care. Neutrino cooling becomes important in late stages. Neutrino cooling is energy lost as weakly interacting particles escape. Like warmth slipping through a thin wall that cannot hold it, Energy leaves without heating the outer layers much. Like a scent passing through cracks, it departs quietly and cannot be trapped. The reason it matters is acceleration. If energy leaks away through neutrinos, the core must contract more to maintain pressure. Contraction raises temperature. Temperature raises burning rate. The interior clock therefore ticks faster. A physical detail grounds this invisible process. The core grows denser. The pressure gradient steepens. Shell boundaries shift inward. The core becomes more compact, while the envelope remains wide and cool. Another payoff arrives gently. A star can appear steady while losing energy rapidly in ways that do not brighten the surface. The surface is not a direct window into the deepest energy budget. A limit of observation is stated softly and precisely. Neutrinos from a distant star are extremely hard to detect. A measurement would rarely capture them before the final collapse. Most inference relies on models and on surface light that lags behind interior change. The limit is therefore indirect visibility and sparse signals. Another payoff follows at once. Even without direct detection, neutrino cooling explains why late stages can race. It also explains why surface changes can be subtle until very late. The narrative shifts again in scale and rhythm. On a surface timescale of days and months, convection and pulsation patterns drift. On an interior timescale of thousands of years, shell burning zones migrate. On a nuclear timescale of millions of years, the star transitions from early stability to late instability. The scale shift remains calm, yet it widens perception. Short surface fluctuations sit on top of long evolution. Long evolution sits on top of an even longer travel time for light across space. Another visual anchor appears. The red disk is seen with gentle mottling. Beneath it, imagined layers tighten and brighten. The outer halo of dust remains. The inner shells shift position like faint rings sliding inward. The physical detail of ring-like layering remains clear yet still soft. A small payoff lands. Late-stage speed does not mean immediate catastrophe. It means the star is moving through a sequence where each step offers fewer options. The sequence can still be long compared with any short observation window. The section closes with a soft transition. Uneven time sets the context for the next checkpoint where limits become sharper. The next step approaches the core's resistance to compression and the thresholds that decide what end state is possible. In the deepest parts of Antares, matter reaches a point where squeezing becomes strangely difficult. The end state depends on whether pressure can resist gravity after the core exhausts its easiest supports. In that region, the story is not about brightness. It is about compression and thresholds. The first unlock is that collapse is not always a freefall. There are forms of pressure that appear when particles are forced too close together. Degeneracy pressure returns as the central concept, yet in a sharper role. Degeneracy pressure is resistance from crowded particles. Like a bookshelf packed so tightly that no more volumes fit, matter pushes back when space runs out. Like sand in a jar that locks into a firm pile under weight, particles jam and stiffen. The reason it matters is fate. If this pressure halts contraction, the core can stabilize as a compact remnant. If it cannot, contraction continues toward a denser outcome. The visual anchor begins as a silent plunge inward. Outer layers fade into warm red haze. Deeper layers sharpen into a steeper gradient of light. Then the glow drops away and the core becomes a dark, compact zone in the mind's eye. Around that compact zone, shells glow faintly like distant rings. The physical detail is a boundary of compression. Density rises rapidly toward the center. Pressure rises even faster. The core's edge is not a surface. It is a steep transition where material properties change. The second concept enters as the driver toward the threshold. Iron core formation becomes relevant without heavy detail. An iron core is a central region rich in heavy nuclei that cannot release fusion energy. Like a fireplace that has turned into ash, fuel is present, but it no longer burns to produce new heat. Like a battery drained to the point where voltage drops, the core cannot power outward pressure the same way. The reason it matters is support. Without fresh fusion energy, the core relies on compression and degeneracy to hold gravity back. A single number anchors the scale of this hidden center safely. The core can shrink toward a size similar to Earth. That is like compressing a vast interior region down to a globe small enough to fit inside one planetary scale. The scale shift is gentle and wide. The visible red star spans an enormous volume. The decisive remnant scale can be closer to a planet. The contrast feels quiet rather than dramatic, yet it is decisive. A small payoff arrives with that contrast. The outer swelling and mass loss are surface stories. The inner threshold is the structural story. A new visual anchor appears and stays unique. A dense sphere sits inside a faint translucent shell. The sphere is surrounded by a thin zone where density falls sharply. Outside layers spread outward again into the vast envelope. The sphere does not glow in the same way. It is defined by gravity and pressure rather than by visible light. The analogy for the section stays unique and calm. The core resembles a deep mattress that has been compressed until the springs can barely move. At first it yields, then it becomes stiff. Further pressure changes the response in a new way. The payoff follows from the mattress image. Resistance grows as compression grows, but resistance has limits that depend on mass and composition. A limit of intuition arrives and is named clearly. In ordinary solids, stiffness comes from chemical bonds. In a dense stellar core, stiffness comes from quantum rules and crowded particles. Everyday hardness is a misleading guide. The limit is therefore intuition about solidity. A second limit of observation follows softly. The threshold conditions are not seen directly because the envelope hides the core. A measurement would rely on surface signals and on models of internal structure. Different model choices can shift the inferred core mass and density. The limit is therefore indirect inference and model dependence. Another payoff arrives immediately. Even with uncertainty, the idea of a threshold is robust. As the core loses thermal support, it must contract. As it contracts degeneracy, support grows. The competition defines whether contraction halts or continues. The narrative moves through a checkpoint from threshold to consequence without building suspense. If contraction halts, a neutron-rich remnant can form. If contraction continues, the outcome can be more compact. The description stays soft and order-safe. The core becomes a place where matter is arranged differently than in any familiar object. The physical detail returns as layering. The transition between regions becomes thinner. Gradients steepen. Shell-burning zones shift inward as the core shrinks. The envelope responds by adjusting pressure and by expanding further. The scale shift widens in time. The inner decision can occur quickly compared with the long life of the star. Yet light travelling outward still carries earlier snapshots. The star can therefore appear unchanged while the interior approaches a limit. A final visual anchor closes the section. The dense sphere remains in the centre of the imagined cutaway. The surrounding shells glow faintly like pale rings. Outside, the red envelope persists as a broad dim sea. The transition remains gentle. The next checkpoint turns outward to companionship and contrast where a nearby hot star changes the local light and geometry around Antares. Antares shares its neighbourhood with a companion whose light feels sharper and cooler. The pairing matters because two different temperatures shape one local space of dust and gas. In that region, red glow and blue-white glow overlap without blending into one. The first unlock is contrast. A red supergiant and a hot companion illuminate the same surroundings in different ways. The visual anchor begins as 2 points in dark star fields. One point is deep red and diffuse at the edge. One point is pale and tight with a harder glare. Between them, a faint haze catches both kinds of light. The physical detail is colour separation. The haze looks warmer on one side and cooler on the other. It looks like a gradient painted across empty space. The first concept is temperature contrast and radiation field. A radiation field is the pattern of light intensity through space. Like two lamps of different colours shining into the same fog, each lamp makes a different kind of brightness. Like morning sun and a cool shaded sky sharing one valley, the illumination splits into zones. The reason it matters is chemistry and dust behaviour. Different wavelengths heat grains differently and can change where dust forms or survives. A small payoff arrives quietly. The same cloud can look different depending on which star's light dominates a line of sight. The second concept enters as geometry of a binary system. A binary is two stars bound by gravity. Like two stones tied by an invisible band, each one moves around a shared center. Like two dancers circling a point on the floor, separation and angle change over time. The reason it matters is shaping. The combined winds and light can carve asymmetries into the surrounding envelope. A single number anchors the system safely. The companion lies about 500 astronomical units away. That gap is like placing the far edge of the solar system between the two lights. The scale shift follows smoothly. The stars are close on a galactic scale, yet far enough that each keeps its own atmosphere. Their influence meets in the space between. A new visual anchor appears and stays unique. A faint bridge of haze seems to arc from the red star toward the pale star. The bridge is not a solid stream. It is a region where outflow and illumination overlap. On the red star side, dust looks thicker, and the glow is softer. On the hot star side, the haze looks thinner and more transparent. The physical detail becomes specific. Dust grains near the hot light can be warmed enough to evaporate or change structure. Gas there can be more ionized, which changes how it emits and absorbs light. Ionized gas is gas with the electrons removed. Like mist turned into a fine spray of charged droplets, it behaves differently in electromagnetic forces. Like a stove warming steam until it changes density and motion heating alters what can exist where. The reason it matters is boundary zones. There can be a sharp transition between dusty and dust-poor regions. A payoff arrives without emphasis. The companion does not need to touch the red star to reshape the surroundings. Light alone can change survival conditions for grains and molecules. A limit of observation appears softly and clearly. At this distance, separating the two sources and mapping their shared haze is difficult. A measurement would depend on resolving a tiny angular separation. It would also depend on wavelength because dust and gas respond differently across bands. Models must infer three-dimensional structure from projected brightness. The limit is therefore resolution and projection ambiguity. Another payoff follows at once. Even with ambiguity, a consistent picture emerges. The environment is not spherical around Antares. It is influenced by a second light source and a second gravitational center. The narrative moves through a checkpoint from geometry to motion. Over time, the two stars change positions around their shared center. The illumination pattern therefore drifts. Regions that are warmed more strongly can shift. Regions where dust survives can shift too. The scale shift widens in time. The orbit takes centuries or longer, while local gas changes can happen over years. A slow orbit therefore writes a long pattern into a changing medium. Another visual anchor steadies the ending. The red star sits inside a soft cocoon of dust. The pale star sits just outside the cocoon's brightest part. The cocoon shows a slightly flattened side facing the pale light. The opposite side looks rounder and thicker. The main analogy for the section stays unique and calm. The system resembles a warm coal beside a bright blue flame. Each light shapes the same smoke in a different way. The payoff lands from that image. Color and intensity differences translate into different heating and different visibility, even when the surrounding material is the same. The transition remains gentle. The next checkpoint turns to the larger space around Antares. Outflow meets the interstellar medium and can form curved fronts and faint shells. The story moves outward without adding new tension. Antares shapes its surroundings without sharp edges, yet a boundary can still appear where flows meet. The wind from the star presses into the interstellar medium and creates a curved front of compressed gas. In that region, emptiness gains structure through pressure and motion. The first unlock is that a slow wind can sculpt a visible shell. The visual anchor begins as a wide view around the red star. A faint arc curves across darkness. The arc is brighter along one rim and softer along the other. Behind it, a thin haze trails outward. The physical detail is curvature and layering. The arc has a leading edge where density rises. Behind the edge, brightness falls in a gradient as material spreads. The first concept is a wind termination region. A termination region is where a stellar wind slows by meeting external gas. Like a river meeting a still lake flow piles up and spreads into a broader front. Like breath meeting a cold window, a thin layer of condensed fog marks the contact zone. The reason it matters is compression. Where the wind slow's density increases and cooling can become more effective. That can make the boundary easier to trace in certain wavelengths. A small payoff arrives quietly. A boundary can form even when the wind is gentle because the space is never perfectly empty. The second concept enters as a bow-shaped structure. A bow shock is a curved front formed by motion through gas. Like the rounded wave ahead of a moving boat, the front forms where material is pushed aside. Like a crescent of piled sand ahead of a steady breeze, the shape records direction and pressure balance. The reason it matters is geometry. The arc can hint at how the star and its wind move relative to surrounding gas. A single number anchors scale without forcing precision. The curved front can sit about 1 light-year from Antares. That span is like placing a whole stellar neighborhood between the star and its outermost carved rim. The scale shift follows gently. A process driven by local wind becomes a structure spanning distances larger than many star systems. Yet the same process begins as particles leaving the star's atmosphere. A new visual anchor appears and stays unique. The arc is seen as a double layer. The outermost layer is thin and bright. The inner layer is broader and dimmer. The outer layer is where compression is strongest. The inner layer is where slowed wind mixes and cools. The physical detail becomes specific. The brightness concentrates along a narrow ridge. The ridge looks sharper on the side facing the star's motion. It looks softer on the trailing side where turbulence spreads material. Another payoff lands softly. Curvature can be a record of balance, not of violence. The front is the place where two pressures match. Wind pressure pushes outward, external pressure pushes back. Where they match, the front holds its shape for a time. A limit of observation is stated clearly. At this distance, the shell is faint and easily confused with unrelated dust structures. A measurement would depend on separating foreground and background emission. It would also depend on wavelength because dust and gas radiate differently. The limit is therefore contrast and line of sight confusion. Another payoff follows at once. Even with confusion, a coherent arc that shares the star's center suggests association. The arc's curvature and symmetry can support a wind interaction interpretation. The story moves through a checkpoint toward the mixing. The compressed front is not a sealed bubble. Instabilities ripple along it. Small waves grow. Fingers of material mix across the boundary. The physical detail appears as scalloped edges and faint knots along the rim. The knots are denser clumps where cooling allows material to gather. The analogy for this section stays unique and quiet. The boundary behaves like a slow-moving snowplow ridge. The ridge forms as a steady push gathers loose material. It becomes thicker where conditions allow accumulation. It becomes thinner where material slips around. The payoff lands from that image. The shape depends on steady pushing and steady resistance, not on a sudden blow. The scale shift widens in time. The front can persist for thousands of years while the star continues to lose mass. Yet the surface patterns on Antares change over days and months. Small changes ride atop a large, slow sculpture. The narrative remains calm and spatial. The arc is not only a boundary, it is also a reservoir where material from Antares joins the wider medium. That medium later feeds other clouds. The section closes with a final visual anchor. The curved rim glows faintly. Behind it, a soft wake trails away as a dim gradient. The red star remains at the center of this subtle geometry. The transition stays gentle. The next checkpoint turns from wind-shaped shells to the deeper reason the end approaches. The star's core eventually reaches a composition that cannot yield more fusion energy. Antares approaches a quiet wall in physics where fusion no longer provides new outward pressure in the center. The end begins when the core becomes rich in iron and cannot release energy by fusing further. In that region, the star's interior runs out of profitable reactions. The first unlock is that fusion has a stopping point set by nuclear binding. Iron core formation is the central concept. An iron core is a central region rich in heavy nuclei that cannot power fusion. Like stacking bricks until the arch can no longer rise without new support, the process reaches a natural limit. Like squeezing a sponge after it is already dry, effort adds strain without yielding more output. The reason it matters is support. When fusion stops, adding pressure at the center contraction must resume and conditions change rapidly. The visual anchor begins as a cutaway that is calmer than it sounds. The outer envelope remains red and wide. Inside a darkened center grows more distinct. Around it, shell zones glow as thin bands. The physical detail is a steepening gradient. Density climbs sharply towards the middle. Temperature climbs as well, yet it no longer produces net energy at the deepest point. The core becomes a compact region with a clearer boundary to the surrounding shells. A small payoff arrives quietly. The star can still shine strongly, while its center no longer earns energy from fusion. Shell burning above the core continues for a time and keeps the envelope luminous. The outer appearance can remain calm while the innermost engine changes role from producer to consumer. A single number anchors scale without forcing precision. The iron-rich core can grow to roughly the mass of the Sun. That is like collecting the weight of an entire star into a region that remains hidden inside the swollen envelope. The scale shift follows gently. A vast red supergiant holds a core whose mass is comparable to an ordinary star, yet packed into a far smaller volume. The narrative moves through a checkpoint from energy to stability. The center loses net energy because iron fusion does not release energy. Instead, energy is absorbed. Photodisintegration becomes relevant with care. Photodisintegration is nuclei broken apart by energetic photons. Like a ceramic tile cracking under intense heat, heavy nuclei can split into lighter pieces. Like ice melting when warmth is applied, the process consumes energy rather than producing it. The reason it matters is pressure. When energy is consumed to break nuclei, thermal support drops and contraction accelerates. Another visual anchor appears and stays unique. The core is seen as a dark sphere surrounded by a thin, bright ring. The ring represents a burning shell still active above the center. The ring's inner edge looks sharper where temperature and density jump. The outer edge looks softer where layers blend into the larger envelope. The physical detail is ring-like layering and edge sharpness. A payoff lands gently. The center can become a sink that absorbs energy while the surrounding shells remain sources. This mismatch drives faster internal rearrangement. The second concept enters with care and remains limited. Electron capture becomes important in dense cores. Electron capture is electrons combining with protons to form neutrons. Like removing support beams from a scaffold, the process reduces electron pressure that helps resist gravity. Like draining air from a cushion, it makes the core less able to push back. The reason it matters is collapse speed. As electron pressure weakens, gravity gains advantage and contraction steepens. A limit of observation arrives softly and precisely. None of these core processes are seen directly through the envelope. A measurement would rely on indirect surface behavior and on models of late-stage interiors. Surface changes can lag behind interior shifts. Dust and extended atmospheres can also mask subtle spectral signals. The limit is therefore hidden causality and delayed indicators. Another payoff follows at once. Even with indirect evidence, the concept of an iron wall is reliable. Fusion up to iron releases energy. Fusion beyond iron does not. The star can therefore be described as approaching a physical ceiling in its central energy economy. The narrative widens in time and scale. The long life of the star spans millions of years. The final approach to the iron wall can occur over much shorter spans, yet still long compared with any brief watching. Light travelling outward adds further delay. The star can therefore look unchanged while the interior crosses thresholds. Another visual anchor steadies the calm. The red envelope remains like a broad sea. Beneath it, the core dark sphere slowly becomes more defined. The thin, bright ring above it tightens. The surrounding shells shift inward. Nothing flashes. everything compresses. The analogy for this section stays unique and quiet. The interior resembles a bank account where deposits stop and only withdrawals remain. The balance can hold for a time because outer accounts still send transfers. Yet the central account no longer earns interest. The payoff lands from the analogy. When the center stops generating net energy, stability depends on borrowing from contraction and from outer shells. Borrowing has limits. The section closes with a soft transition. The iron wall does not announce itself at the surface with a sudden sign. It changes the interior budget of pressure. The next checkpoint follows that change into the very last moments of core stability where collapse becomes unavoidable and the outcome depends on how the envelope responds. Antares holds a final tension where the center contracts faster than the outer layers can respond. The last stage begins when pressure support fails in the core and collapse becomes a rapid inward sweep. In that region, the star's end is decided by how quickly the core compresses and how energy escapes. The first unlock is that collapse is a process of timescales, not a single instant. Core collapse is the central concept. Core collapse is rapid contraction after pressure support weakens, like a tall stack of sandbags that suddenly slumps when a lower layer shifts. The structure can change quickly once a threshold is crossed. Like a dam gate released after years of steady pressure, motion accelerates because restraint is removed. The reason it matters is coupling. The core can change far faster than the envelope, so the surface may not warn of the internal rush. The visual anchor begins as a calm cutaway that suddenly tightens in imagination. The outer red envelope remains broad and dim. The inner shells appear as faint rings. Then the central region contracts inward and the rings slide closer together. The physical detail is steepening gradients. Density rises sharply, pressure rises sharply. The boundary between core and surrounding shells becomes thinner and more distinct. A small payoff arrives quietly. Collapse can begin and while shell burning still exists above the core because the center no longer gains support from net fusion. Another payoff follows without emphasis. The collapse is fast because gravity scales strongly with density in the center. As the core shrinks free, fall time shortens and contraction accelerates. A single number anchors the timescale safely. The deepest collapse proceeds over about 1 second. That is like the time between two calm breaths, yet it transforms a core that took millions of years to build. The scale shift lands gently. A second is tiny in daily life. In a collapsing core, a second is long enough for matter to traverse a planet-scale distance at extreme speeds. The narrative stays calm and precise. As the core contracts, electron capture continues. Neutrinos carry away energy. The core cools in the sense that energy escapes without heating the envelope. A limit of intuition appears and is named clearly. The idea of a rigid object falling inward fails because the core is not a solid. It is a fluid of nuclei and particles. Pressure and composition change continuously during the fall. The limit is therefore mechanical intuition. A limit of observation follows softly. The collapse itself is hidden and brief. A measurement would almost never capture direct signals until an explosion or a neutrino burst. Surface light arrives later and can be delayed or altered by surrounding material. The limit is therefore timing and visibility. Another visual anchor arrives and stays unique. The collapsing core is imagined as a shrinking dark sphere with a bright compression front. The front is not a flame. It is a boundary wherein falling material piles up and stiffens. The physical detail is a shock-like layer that forms and stalls. Shock formation is the second concept and it stays minimal. A shock is a sudden jump in pressure and density, like a traffic jam that forms when lanes narrow in falling layers stack up and create a compressed front. Like a wave that steepens when it enters shallow water pressure, changes abruptly at the boundary. The reason it matters is outcome. Whether the shock revives or fades affects what the envelope experiences. A small payoff arrives gently. The shock does not guarantee an explosion on its own. It can stall because energy is spent breaking nuclei and because neutrinos carry energy away. The description remains soft and order safe. The shock sits at a boundary and hesitates. material continues to fall through outer layers. The core becomes extremely compact, the outer shells are still far away on the same second scale. The scale shift widens. The core changes in a heartbeat. The envelope changes over hours to days if an outward wave forms and travels. Light from the surface can change later still because photons scatter through extended gas and dust. Another payoff follows from the shift. A distant observer can see a long, steady red glow right up to a short internal transition because the causal chain must travel outward through layers. The analogy for this section stays unique and calm. The collapse resembles a book being shut quickly after a long, slow reading. The closing action is brief. The story inside the pages was built over time. The payoff lands from the analogy. The final motion is short, yet it depends on the whole previous structure. The physical detail returns as layering compression. Ring-like shells slide inward, gaps narrow, gradients steepen. The central region becomes a compact core that may rebound slightly and send a pressure wave outward. The rebound is not framed as drama, it is a mechanical response. A final visual anchor closes the section. The dark sphere contracts and then steadies. A pale wave begins to move outward through inner shells. The wave is faint at first, becomes a broader front as it enters lower density layers. The transition stays gentle. The next checkpoint follows that outward influence into the surrounding envelope, and the local environment where matter already lost by Antares can shape what emerges and what remains. Around Antares' loss becomes a kind of quiet construction where expelled gas and dust turn into a wider pattern across space. The long consequence is that material leaving the star does not end. It changes form and location. In that region, an ending inside the core becomes a beginning in the surrounding medium. The first unlock is that enrichment is a slow drift rather than a single event. The visual anchor begins far outside the red disk. A broad, faint halo surrounds the star. Within the halo, thin streamers arc outward. Some streamers are denser and slightly darker. Some are thinner and more transparent. The physical detail is filament and gradient. Each filament has a sharper inner edge and a softer outer fade. The inner edge marks where density rises, the outer fade marks where particles spread. The first concept is mixing with the interstellar medium. Mixing is the blending of outflow with surrounding gas. Like ink released into still water, dense patches stretch into ribbons and then soften into a uniform tint. Like warm breath fog that thins and disappears into cooler air, structure spreads until only a faint trace remains. The reason it matters is reach. Material from one star can become part of a much larger reservoir. A small payoff arrives quietly. Even when the star's surface looks unchanged, the surrounding medium continues to gain mass and complexity. The story moves through a checkpoint from near to far. Close to the star, dust grains form in cooler pockets. Farther out, grains drift into thinner space where collisions are rarer. Some grains survive, some grains fragment, some grains are warmed and altered by local radiation. The physical detail stays concrete. Grain-rich regions look slightly thicker. They absorb more light and scatter it differently. Their edges look soft because the cloud is not a solid wall. A second visual anchor appears. A faint ring-like band is seen in the halo. The band is not a perfect circle. It is slightly lopsided and clumpy. It suggests an episode of stronger loss that has now expanded outward. The payoff follows from the band. The surrounding space can preserve a time record. Each shell is a past outflow episode written as a thin layer. The second concept enters with care. Dust is a solid particle made from cooled atoms. Like powdered stone carried on a slow breeze, dust travels without needing pressure, support from heat. Like frost crystals that persist in shade dust can endure where gas alone would disperse quickly. The reason it matters is seeding. Dust surfaces help molecules form. Dust also helps cool clouds by radiating heat away. Cooling allows gas to clump more easily under gravity. Another payoff lands softly. The star does not need to create a new cloud from nothing. It only needs to add ingredients and cooling pathways to what already exists. A single number anchors the timescale safely. The outflow can take about 10,000 years to spread across a region a light year wide. That span is like the time it takes a slow river to carve a new bend through soft ground. The scale shift stays gentle. The core can change over a short interval. The surrounding medium carries that change outward over millennia. The result is a delayed footprint. The environment evolves long after the interior threshold is crossed. A limit of observation arrives softly and clearly. The three-dimensional structure of the halo is hard to recover from projected brightness. A measurement would depend on how light scatters through dust along the line of sight. A measurement would also depend on assumptions about grain sizes and temperatures. The limit is therefore projection and model dependence. Another payoff follows at once. Even with uncertainty, repeated patterns can still be trusted. Filaments and arcs imply flow, shell-like bands imply episodes, gradients imply dispersion and mixing. The narrative widens to chemistry without adding density. The outflow contains elements built in earlier burning stages. It also contains material processed in shells. When that material cools, atoms combine into simple molecules. Molecules then travel with dust in the expanding halo. The physical detail returns as layering. A cooler outer zone holds more stable molecules. A warmer inner zone holds fewer. The boundary between them is a temperature gradient, not a sharp fence. The analogy for this section stays unique and calm. The environment behaves like a slow loom. Threads of outflow are woven into a larger fabric of the surrounding medium. The weave is uneven at first. Over time, it becomes smoother as threads spread and overlap. The payoff lands from the loom image. The final pattern is not one strand. It is the accumulation of many gentle releases that blend into one background. The scale shift widens again. A single star's halo is small compared with a spiral arm, yet many stars contribute similar halos over a long time. Their combined material changes the composition of the medium across a region. The consequence is gradual. The change is persistent. Another visual anchor steadies the ending. The halo is seen as a dim bowl of light around Antares. Within the bowl, dark knots drift outward. Each knot trails a faint tail that softens into the background. The tails align loosely with the direction of motion through the medium. The physical detail is tail and curvature. The tail is narrower near the knot. It widens as it fades. A final payoff arrives gently. The surroundings keep the memory of the star's life in matter, not in light. That memory persists even when the surface glow dims or changes. The section closes with a soft transition. The next checkpoint turns from consequences to quiet resolution. The final view steps back to place Antares in a wider, calm context of time distance and gentle continuity. Antares remains bright in the sky, while its most decisive changes stay hidden far inside. The quiet truth is that the star is already a story told with delay and distance. At this distance, light behaves as a time capsule. The first unlock is simple. Seeing Antares means seeing it as it was in the past. Antares sits about 550 light-years away. That span is like the familiar 8-minute delay between sunlight and Earth, stretched into centuries. A soft visual anchor begins with the red disk itself. The edge looks less like a line and more like a blurred rim. The rim fades into a thin haze. The haze is not uniform. It is thicker in some directions and thinner in others. The physical detail is a gradient in brightness around the limb. The gradient hints at dust and gas near the star. It also hints at uneven outflow. The first concept is light travel time. Light travel time is the delay between emission and arrival. Like a ripple leaving a pebble and reaching the far bank later, information spreads at a fixed speed. Like a scent spreading through still air and arriving slowly at distant layers, change is felt later than it occurs. The reason it matters is timing. Surface light can lag behind interior transitions in the sense that the message takes time to cross space. A small payoff follows. A distant view can remain calm even when internal thresholds have already passed. The scene widens into the surrounding halo. A faint bowl of scattered light surrounds the star. Within it, dust forms soft veils. Some veils show curved edges, some veils show thin threads. The physical detail is filament and curvature in a diffuse medium. The filaments look sharper on one side and softer on the other. That asymmetry suggests motion and mixing. A second payoff arrives. The environment stores a layered record of past loss. It does so without needing a single dramatic event. The second concept enters as perspective across scales. Scale shift appears gently. A grain of dust is tiny. A dust veil spans distances larger than many star systems. Both belong to the same outflow. The veil drifts outward over long intervals. The star's convective surface changes over short intervals. The same system therefore holds rhythms from days to thousands of years. The visual anchor shifts closer again. The red photosphere is imagined as a soft surface with mottled patches. The patches are not static. They drift and reshape. The boundary between bright and dim regions is irregular. The physical detail is mottling and edge texture. A payoff lands quietly. Surface variation can change brightness without changing the long-term fate. It can be weather on a star. The large evolution remains governed by interior structure. A limit of observation arrives softly and clearly. The interior core cannot be seen through the extended envelope. Any inference must rely on models and indirect surface signals. Those signals can be masked by dust and by complex atmospheres. The limit is therefore hidden causality and weak indicators. Another payoff follows. Even with hidden interiors, the broad path is stable. Massive stars expand, lose mass, and approach core collapse after fuel stages are exhausted. That stability comes from nuclear physics and gravity, not from surface appearance. The scene moves outward to the wider region around Antares. A curved front in surrounding gas remains faint and broad. Its rim is slightly brighter along one arc. Its wake is softer behind. The physical detail is a compressed edge and a trailing gradient. The arc marks where outflow meets external gas. It marks where pressure balances for a time, scale shifts again. That arc is far from the star compared with the photosphere, yet it is near compared with the spiral arm of a galaxy. The environment therefore sits between two immensities. It sits between the star's interior and the Milky Way's long lanes of gas. A calm analogy settles the ideas. The system resembles a tide moving between a quiet bay and the open sea. The exchange is steady. It is not always visible in one glance, yet the shoreline changes slowly as water moves in and out. The payoff lands from the tide. Material leaving Antares joins a larger reservoir. That reservoir later reshapes other clouds. The star's loss becomes part of a longer circulation. The visual anchor becomes the Milky Way background. Dense star fields form a faint band. Dark lanes cut through the band as soft shadows. Antares sits near those lanes with its red glow. The physical detail is contrast between bright fields and dark dust lanes. The lanes are not empty. They are colder and denser regions that absorb starlight. Another payoff arrives. The same dust that dims background light is also the medium that can form new structures when cooled and compressed. The narrative remains calm about the near future. The exact timing of a final explosion cannot be predicted precisely from a distant view. Models offer ranges rather than a clock. Surface behavior is not a reliable countdown. The limit is therefore predictive uncertainty. A gentle closure follows without suspense. Whether change comes sooner or later, Antares already shapes space through steady outflow and slow mixing. The red light continues to travel outward. The dust continues to drift and thin. The wider galaxy continues its quiet rotation. In that region, the star is both a present glow and a delayed message. The last image rests on stillness. The red point holds steady. The surrounding haze fades into darkness by degrees. The story ends as a soft continuity of light and matter.